Welcome to the fourth video in this third class session of videos. We're now embarking on perhaps the most difficult part of our discussion of atomic theory, and we're going to hit something called hybridization, and hopefully seeing it this time around in organic chemistry versus your introduction to it in general chemistry will help elucidate it or help you understand it a little bit better. We'll go ahead and look at beryllium hydride. So by the valence shell electron pair repulsion theory, we know what the hybridization on beryllium is if we're told it's a linear molecule. So if it's a linear molecule, we automatically know our knee-jerk reaction from general chemistry should tell us, the hybridization on beryllium must be sp. But we really don't understand what that means. Maybe not to the fullest extent that we possibly could at this point. Similarly, in VSEPR, trigonal planar would imply an sp2 hybridization. Tetrahedral would imply sp3 hybridization. So let's try to figure out what this means from the organic chemist's perspective. If we look at beryllium, its ground state electronic configuration is 1s2, 2s2. The 2s orbital is full. Let's try another configuration for bonding. Why don't we promote one of the electrons in a 2s orbital up into a 2p orbital? So we'll have beryllium in this electronic configuration, 1s2, 2s1, 2p1. So here we have beryllium. Beryllium's going to be at the center of that sphere and p orbital. The sphere is the 2s orbital. Of course, there's an inner shaded region that I haven't drawn because we all remember that the 2s orbital is a jelly donut. But we're going to try to, use the 2s atomic orbital and one of the three 2p atomic orbitals to bond to the two different 1s orbitals of our two different hydrogen atoms. And so if we try to do that, I glommed one of the 1s's onto this lobe of the p orbital, and then I glommed the other 1s onto this sort of nicely, lightly shaded section of the 2s orbital that isn't interfering with that dark shaded section of the 2p. This is a bent molecule, right? It doesn't make any sense. And so that's why we have to go through this wicked process of hybridizing our beryllium first. So we need to make a hybrid of two atomic orbitals on beryllium first. And just like forming molecular orbitals, when you form hybrid atomic orbitals, well, the number of atomic orbitals that you begin with equals the number of hybrid atomic orbitals that you form. So let's see that with beryllium hydride. So what are we going to do? We're going to combine a 2s atomic orbital with one of the three 2p atomic orbitals on beryllium. So here's a 2s, here's a 2p. I'm going to combine these two. I'm starting with two atomic orbitals, and what I generate is two hybrid atomic orbitals. And what are they? They're sp hybrids. So there are two sp hybrid atomic orbitals. Now the little center of, well, it's not really the center, the inflection point where our wave function sign changes from positive to negative, that's where the nucleus is, right? So I'm showing these two orbitals sort of separated, but the two atomic orbitals on beryllium share the same nucleus, right? So really, these things sort of overlap because they share the same nucleus where the pen is pointing. And what's interesting is the shape of our sp hybrid. There is a big sort of white lobe on one side and a little itty-bitty black lobe. It's all relative. It could have been a big black lobe on one side and a little itty-bitty white lobe. Anyways, it's nice, it's convenient that sp orbitals look like sp2 orbitals look like sp3 orbitals. They all have a big sort of lobes part and a little itty-bitty back lobe. Well, our two sp orbitals are going to be pointing, the big lobes at least, in opposite directions, overlaid on the same nucleus. And so what does this look like from an energy diagram state? Well, in our pre-hybrid state, this is beryllium not in the ground state. It's in that sort of state where we promoted one of the 2s electrons up to a 2p electron. But what we're going to say we're going to do is we're going to take one of these 2p orbitals and the 2s orbital, and we're going to form two sp orbitals, sp hybrids. What are we left over with? We're left over with two empty 2p atomic orbitals. Just because they're empty doesn't mean they don't exist. Just because the glass is empty, not filled with water, doesn't mean the glass does not exist. You can still fill that glass with water at some point. What we're going to do with these hybrid sp atomic orbitals is we're going to combine each sp with a hydrogen 1s. And so if we do that, we're really combining two hybrid sp atomic orbitals with the two 1s atomic orbitals. So we form a total of 4 molecular orbitals. 2 of them are going to be bonding molecular orbitals, and 2 of them are going to be anti-bonding molecular orbitals. And then of course our empty 2p orbitals really fit in the middle in terms of energy, and they're empty. So I mean, geez, beryllium hydride is a Lewis acid because it's got empty 2p orbitals. I've drawn a picture of the 2 sigma bonding molecular orbitals in beryllium hydride. So if you could see in X-rays and electron density, this is what you would see for the beryllium hydride molecule. There's the nucleus, the beryllium nucleus. This is a bonding beryllium hydride bond. Similarly, this is another bonding BEH sigma bonding molecular orbital. Now, what I've not drawn on this are the empty 2p orbitals. One of the 2p orbitals would be in the plane of the page, one lobe going up and one lobe coming straight down, which would be of opposite phase. And another empty 2p orbital would be coming out of the plane of the page, one lobe coming out and then one lobe going back behind the plane of the page, oppositely phased. What's drawn over on the left are the 2 anti-bonding beryllium hydride molecular orbitals. And you can see that there are nodes between the hydrogen nuclei and the beryllium nuclei. So pretty complex stuff and a lot to digest at once. Our next example will be borane, and then we'll move on to methane, and then we'll do some even more complex molecules, and we'll even learn to put together crude molecular orbital diagrams at some point. Anyways, it's nice to know that in terms of relative orbital energies, antibonding are going to be higher than non-bonding. That would be things like the empty 2p atomic orbitals. They did not participate in bondings, and they were sort of in the middle in terms of energy. And the lowest energy molecular orbitals, of course, are going to be our bonding molecular orbitals. Like I said, it's nice that sp hybrids, sp2 hybrids, and sp3 hybrids all have a similar shape, one big gigantic lobe and one tiny little itty-bitty back lobe. In terms of the hybrids, we could look at percent %s character and percent %p character. For an sp, I mean, it's pretty equal percentage character, right? 50% s, 50% p. This describes linear molecules that are, greater than diatomics, that we're talking about, triatomic and higher. So hybridization on A here would be sp if it's linear. For sp2 hybrids, we've got a 33% s because we're one of 3 parts, 67% p. Those would be characteristic in terms of hybridization for trigonal planar molecules of the type AX3. And of course, sp3 hybrids would be 25% s character, 75% p, and that describes tetrahedral molecules of the type AX4. Typically, there's no hybridization on diatomics. They're simply linear, and we don't hybridize the s and p orbitals. That pretty much finishes it for this particular video, and like I said, we'll go ahead and look at a few more examples to solidify our understanding of this weird hybridization of atomic orbitals and using those hybrids to give molecular orbitals and form molecules.